Alright, so today in class I had done a screencast as we worked along in class on the step-by-step process of going through solving a finite element solution. In this case, for a four element of linear elements equally spaced, um, the problem we had written down on the board, so it should be in your notes. I made a mistake such that the final answer wasn't correct, so I wanted to correct that now, and I'll just go through the whole process again. So again, the domain of the problem is from x equals 0 to x equal 1, four equally spaced elements. If I break out a single element, then define its own element coordinate system, xe, that goes from 0 to 1/4. The first thing we need to do is develop the shape functions for an element so that we can develop the stiffness matrix. So for a single element, linear interpolation 1, x, then we want to create that so-called A matrix, which is big X evaluated at 0 and big X evaluated at 1/4. Then the element shape function is then X times inverse A. There we have it. Okay, so the element stiffness matrix is then defined over the domain of the element. I'm going to take the derivative of the shape function I with respect to x, multiply that by the derivative of the shape function j with respect to x, subtract shape function I times the shape function j. And again, this should just be in your notes. That's how we define the shape function, the element stiffness matrix. And of course it is a matrix, so we need to evaluate these ij's. For two nodes, we say I goes from 1 to 2 and j goes from 1 to 2. So when I showed you this, guys, in class, I think we used two do loops to create this. Another way to do it in Mathematica is to use this table feature. So there we have an element stiffness matrix. Now we want to assemble that into the global stiffness matrix, which will start by allocating the space for it. Just going to make a constant array 5 by 5 of zeros. So I'm just created a matrix of zeros to allocate the space. For a K matrix, just like that. Okay. So then what I want to do is I want to put, for the first element, the element stiffness matrix will go in this position here. Then for the second element, this position here. Third element, this position here. And the fourth element, this position. Okay. So I can do that in Mathematica just by saying I want to go 1 to 2 along the row, 1 to 2 along the columns, and I'm going to add in KE. Okay, and I can do this 4 times for all the elements. So the element that goes from 2 to 3, the element that goes from 3 to 4, and then if we look at what K looks like now, see, looks like that. Okay. Alright, so now we have to do something a little different for the force quantities, because again, the force is defined in terms of x, which is a global coordinate, right? And so we need to integrate over bounds of each element that correspond to the global coordinate. And that also means we need to redefine the shape functions in terms of the global coordinate. Here they were done in terms of the element coordinate. So for the first one, it doesn't change. We're going to go from x0 to a quarter. I guess first of all, let's define a constant array to allocate space for the force vector. So just a vector of zeros. So then we're going to go from 1 to 2. We're going to add in over the domain of the first element, 1 to 2, we go from 0 to 1/4, and then the function there is x squared times n I. So we need to make this a table that goes from I 1 to 2. And I made my common mistake of not putting 2 n's in there. There we go. So there we have the force vector for the first element. We'll have to redo this for the second element, this time putting in the proper bounds. So from 1/4 to 1/2, element 2 to 3, 1/4 to 1/2. Okay. Do this again for the next element. This time it goes from 1/2 to 3/4. It's the element between node 3 and 4. Again, 1/2 to 3/4. And finally, 3/4 to 1. This is the element that goes between 4 and 5. 3/4 to 1. So now if we look at what F looks like, we have that. Okay? Now, when we apply the boundary conditions, which we had written up on the board, u at 0 is equal to 0 and u at 1 is equal to 0. Of course, u at 0 corresponds to node 1, which means we can cross out or cancel out the first column and the first row of the K matrix and the force vector. U at 1 equal to 0 corresponds to the fifth node, which means we can cancel out the last row and column of the K matrix and the force vector. So in Mathematica, the way we would do that is if we look at the K matrix, we'd say drop the first row, and then if we transpose that and say drop again, and then transpose it back, that will have canceled out the first row and the first column. Okay, so we had a 5x5, now we have a 4x4. We can actually do this one more time. We'll call this K new, and we're going to say drop. Okay. This time we're going to take the last row, -1 in Mathematica means last row. Okay. We're going to do that twice, -1 for the last column. Okay. So now we have a 3x3. Well, with a 5x5, we took the first row off and the last row off, and now we have a 3x3. And you can see that it corresponds to this 3x3 here. So if you look at that, and look at that, they're the same. Okay. So we need to do the same thing for the force vector. This time we just drop the first term and the last term. So we'll just say drop the first term in the last term. We have that. Now we can solve this. Alright, so there's our solution. If we want to add in the two boundary conditions to make the solution more complete, we can do that by saying, you remember that u at 0 is 0, combine that with the solution at the interior nodes, and then u at 1 is 0, so that we get this. And then we can plot this. We make a table that goes from I minus 1 times a quarter sol I, where I goes from 1 to 5. Alright, so we just made XY pairs. 0, 0, a quarter in that number, a half in that number. Okay. So then we can plot this. And that is, in fact, the correct solution. You can verify it by solving the differential equation numerically. In Mathematica, at these nodal points, it should be very close to the actual solution. And if we took more nodes, we would get something representative, or took more elements, then we'd get something very representative of the exact solution. Okay, sorry about the mistakes I made in class. This should help clarify everything.